in terms of when we talk about body forces, of course, which is defined using FB. FB refers to the body forces. We need to evaluate the body force matrix in the natural coordinate system in order to evaluate the body forces acting on the system. I will directly write down how we can evaluate these body forces, at least how the computer program evaluates the body forces. And for this, you need to do triple integral over the volume, use the shape functions, and of course, use the body forces expressed in the global coordinate system here. And we need to express now this coordinate, the body forces in the natural coordinate system S. So this equation, we know the volume can be expressed as a function of, let's say, sectional area and the thickness. So the term dV can be expressed as A times dx. So when we substitute this in the body force integral matrix, then you would end up in getting, okay, since A, the cross section of this bar element is constant, we can take it out from the integral, and we need to still evaluate this matrix coordinates over the length of the element. Since we already know n1 and n2, which enters inside the shape function, we have already obtained a relationship with this, and we already know the relationship between dx and ds, that the relationship is given between dx and ds by L by 2. Of course, dx is equal to L by 2 times ds. We can use this information and rewrite equation 7.1.18 by substituting these values and expressing the body forces. A, we have to evaluate the integral. Now we move on to the S coordinate system. So we need to closed integral, or do the closed loop integral, and of course at the same time do the transformation or the mapping. So xb has to be multiplied by L2 divided by L divided by 2 to transform into the S, let's say, S domain. And inside the brackets we have the two shape functions, again, which are function of the natural coordinate system. These are the n1 and n2 values which we previously obtained. Okay, so I have simply substituted the n1 and n2 as well as the relationship between the two coordinate system for evaluating the integral given by equation 7.1.18. And on integration of this equation, on integrating equation 19, what you would get is the body force matrix would be equal to AL by 2 XB. So the physical interpretation of the body force matrix is that since AL kind of represents the volume of the element, this is the volume of the element, and XB is the body force per unit volume, then these all ALX terms, ALXB term gives the total body force acting on the element. Yeah, so this is the physical interpretation of this equation. ALXB gives the total body force acting on the element. What is this factor 1 by 2 represents here? The factor half indicates that this total body force is equally divided or equally distributed among the two nodes of the elements. Okay, so this is the physical interpretation of the equation 7.1.20. So whenever we have surface forces, again we need to now do a transformation, because previously also for the body forces we expressed all the forces acting per unit length in the using the x coordinate system. So we need to apply the transformation. So when we talk in terms of, let's say, surface forces such as traction forces, surface forces, what did we use? We used the following equation to express the surface force matrix. We have to perform an integral over the surface, double integral, that is over the surface. Of course, multiply with the shape functions, the forces per unit length times ds. So if you assume a constant cross section, and of course the uh, uh, traction within the element is uniform over the, let's say, total length of the element, we can say we can perform the integral, or we can reduce this integral to uh, perform the closed loop integral over the length L. Of course, since this traction is constant over the length, we can reduce this integral to 7.1.22. Yeah, so now we can assume, of course, t hat x is expressed in terms of unit of force per unit length, and by assuming the shape functions to be n1 and n2 and n2, and substituting from the previous equations, we know these two shape functions n1 and n2 are 1 minus s divided by 2 and 1 plus s divided by 2. We can simply substitute the equations for the shape functions in order to obtain the body forces and evaluate the integral. Now we are operating in the s domain, coordinate system, and the relationship between the x body forces acting per unit length has to be multiplied by L by 2 to express in terms of the x coordinate system, sorry, the s coordinate system. And the shape functions can be written, the two shape functions n1 and n2 has to be integrated over a length of, over a domain of -1 to 1 in this domain. So on integration of this equation, what you would get is the total body force acting on the element, the total surface force acting on the element would be, since tx is, let's say, constant, we can take it out because it's uniform over the length, L is constant, and once you do the integral, you would end up in getting result. Here again, the physical interpretation of equation 7.1.2, 1.24 is that now the Tx is expressed as the force per unit length, and Tx times L gives the total surface forces, total surface force acting on the element. And again, the fraction here, this indicates that the uniform traction force is equally distributed to among the two nodes of the element. It is interesting also to note that, because in order to evaluate this integral, we assume that the traction forces along the length of the element is constant. Yeah. So, but if the Tx or the traction force is a function of x, or meaning in these terms, if it's a function of s, then the corresponding force allocated for each node will not be equal. And of course, this can be found by conducting the, or evaluating this integral. What I want to say is that the division of the total surface force not be equal, it will not be equal to it will not be equal among the two nodes. It would differ if it is a function of the length of the O in this case, or if it's a function of S. So since we have already have an idea about how the isoparametric formulations can be applied to a simple bar element, and also we have also used the isoparametric formulation to express the body force as well as the surface forces. we are equipped with all the relevant equations to perform a complete evaluation of a finite element problem using isoparametric formulation. Let's try to further complicate this problem now to see the real advantage behind this isoparametric formulation of the system. So let's consider a plane stress element. Let's consider a rectangular plane stress element. And let's try to develop, let's say, the element stiffness matrix. And later onwards, let's try to see, apply isoparametric formulation, let's say, for this particular element, to see how we can apply this concept to slightly larger elements, or let's say complicated elements having large number of degrees of freedom. So there are certain advantages, mainly two advantages of using rectangular elements over triangular elements. They are the ease of data input, especially when we talk in terms of the computer programming aspects, and of course the interpretation of the stresses quite simpler than when you're analyzing a problem which is modeled using triangular element. Of course, there's a disadvantage when you're using a rectangular element, is that because the rectangular element is associated with straight sides here. They are associated with straight linear displacement triangles. So there we can only observe linear displacements of straight edges. So this can be this can really affect the real model, or the real conditions. So because the edges are straight and the linear displacements are quite straight when we talk in terms of a linear rectangle. So this is not always the case when we think in terms of triangular elements, because the small triangular elements can be implemented to even a rectangular element can be really subdivided into, let's say, small triangular elements to capture even the finest displacement on a certain location, on a certain edge. So those are the advantages as well as the disadvantages when we talk in terms of different type of parameters. So what we try to do is, let's try to derive the element stiffness matrix for a rectangular plane stress element. So before we move on to the isoparametric formulation of the system, let's try to derive the element stiffness matrix using the global coordinate systems, just like we did in the previous sections. So first step is, of course, the selecting of the element. Step 1, element selection. We have a rectangular element, or let's say a rectangular element, the following rectangular element. And of course, we do have the coordinate system. So the simple plane stress rectangular element has 4 degrees of freedom. Let's write down the nodal degrees in the counterclockwise. So 1, 2, 3, and 4. I have represent or label the nodes in the counterclockwise manner. And the coordinate system is x and y. The corresponding displacements in the direction x is given by u, and the y in y direction is given by b. So at each node, the displacements can be given as in the x direction as well as positive y direction, u2 and b2. And let's assume that the width, the length of the rectangular is b, so equally placed 2b, and the length, the height, so the width is given by h, so 2h. We have considered, let's say, all interior angles to be 90 degrees. Of course, this is not a skewed plane stress element. For the simplicity, of course, we have used this all interior angles as 90 degrees, and of course the base and the height of the dimensions are 2b and 2h, and at the very center we have placed the origin for the coordinate system. And the unknown degrees of or nodal degrees of freedom or the displacement matrix is given by each node has 2 degrees of freedom, u1 and v1. So there are 4 by 2, that is 8 degrees of freedom, unknown degrees of freedom. We have defined the unknown degrees of freedom in that step 2. In the next step, we would like to introduce the displacement function. Let's call it as usual selection of the displacement function. So we are interested in describing the displacement in the y direction, x direction, as well as the y direction using linear displacement. So the linear displacement functions. So why we select linear is so that the compatibility conditions between the different boundaries between the edges would be satisfied using a linear function. Since of course, since they are connected in two nodes, linear function would be the best to describe or satisfy the compatibility conditions, of course. So u is a function of x comma y, and since each node has, let's say, 2 degrees of freedom, and there are 4 degrees of 4 nodes, there will be 8 degrees of freedom, meaning we have 8 unknowns. So u can be expressed. These steps are quite familiar to you now because we have already done it over and over again. And so I will directly write it a3y and a4xy. Similarly, the displacement in the y direction is a function of x and y, a5, a6x, a7y, and a8x and y. So 7.2.2. We can follow the same usual procedure to eliminate, let's say, or to find a1 or a1 up to a8 by substituting the nodal coordinates. And if you do it correctly, the displacement functions you would end up in getting the following displacement function. I will simply write it down. You can try it on your own. You have to simply substitute. You have to simply evaluate u1, of course, up to u8 and v1 to v8 by substituting the corresponding nodal coordinates. So if you do it correctly, you will be able to find express the function displacements function u and v in terms of the u1s and u's and i's, which you find by substituting the coordinate systems, the nodal coordinates. So u1 would end up in getting a function. Now these are all related via the coordinate systems and the geometric, of course, the shape of the element. Similarly, this is the function that you would get, and we can now express equivalently in terms of the shape functions, because these displacement expressions now we can use. We can separate the variables and express in terms of the shape functions. So the displacement function can be separated now into shape functions, of course, and express it in a more convenient way. The corresponding shape functions which you would get is, of course, you can see now if you separate the u's, you would end up in getting these functions as the corresponding shape functions. Would be b minus x times h minus y for bh. Yeah, you can see from this relationship here. Similarly, n2, b plus x h minus y for bh, n3 is equal to b plus x h plus y for bh, and 4 is equal to b minus x h plus y. Here you have nicely separated the shape functions, and now the displacement function, which is matrix described by u and v, can be separated or expressed by the displacements of nodes 1 up to nodes 4. Each node has 2 degrees of freedom. And of course, it is a multiplication of, let's say, the shape functions. So what is the next logical step? Step 3 is to define the stress strain relationship. Strain and strain displacement relationships. Let's try to apply these relationships. The next logical step. So again, we are dealing with a two-dimensional element. So there will be two-dimensional stress elements. Of course, it will be a two-dimensional stress trait, meaning the stress matrix will have 3 contributions coming from the strains in the x direction, y direction, as well as the shear strain in the xy plane. So how can we evaluate it? The evaluation of these strains is by obtaining the derivative of the displacement in the x direction and in the y direction, and of course the rotation is obtained by the following. Using these derivatives, because like say by taking the derivatives of u and v, we can express the strains using the unknown nodal displacements. For this, we can use the equations which we just derived, the shape functions, of course. Since we know the strain is related via the B matrix, the element matrix, to the D matrix. Yeah, here the B matrix, we can obtain the B matrix, of course, yeah, by the following relationship. To write down, it's quite lengthy equation when you do, but I will write down so that you can take your own time and see whether you obtain this matrix on your own. You can use this following equation or the shape functions which you just described, and since the functions for u and v are given here, you can obtain the corresponding derivatives. So once you obtain the corresponding derivative and also separate the displacement function, you would get the B matrix. Yeah, the element matrix. So the element matrix you would get would be, there would be a common term 4 times BH. I will write down, you can try it on your own, okay? So this term would be minus h plus y. Let's try to, yeah. So once we have this B matrix, then in the step 4, what we need to do is we can directly evaluate the stiffness matrix and equations. So we can derive the stiffness matrix, derive element stiffness matrix, that is K. How? By obtaining the integral, double integral, of course, we know the element matrix, the constitutive matrix, and of course multiplied by the element matrix thickness of the element, and dx times dy, double integral from dx has to be performed from minus b to plus b, dy has to be performed from minus h to plus h. Yeah, so by evaluating this integral, and of course using the correct constitutive matrix depending on the plane stress and plane strain conditions. If you can remember, there's a slightly 2 different versions for plane stress and plane strain conditions. And now, since the B matrix is also a function of x and y, you can do the integration and obtain the element stiffness matrix for a rectangular element. And as it should be clear that the element stiffness matrix for this rectangular plane stress element, of course, element should be an 8 by 8 matrix because there are 4 nodes and each node has 2 degrees of freedom. Finally, since we have dealt with the element stiffness matrix, the element force matrix will be given, as you can see, by the summation of the body forces as well as the surface forces. For evaluating the body forces, we need to obtain the integral over the total volume, which is a transpose of the shape function, the body force matrix, or force applied per unit volume, times dV, external pressures applied, and of course the forces, the surface forces, the shape function, the transpose of the shape function has to be multiplied by the fraction forces acting on the surfaces and integrated over the new uh, natural coordinate system. So here we know that the capital N, the shape function, is a rectangular matrix, and we have values from n terms ranging from n1 to n4. So simply, since we have the force matrix and of course the element stiffness matrix, we can extract the corresponding displacement using this relationship given in this equation 7.2.12. The remaining steps for these elements are quite same, of course. If you can recollect what we did for calculating stresses using the concentric triangle element matrix. So it's important to note that when we consider the rectangular plane stress element, the stresses within this element now vary in both x and y direction. Yeah, you will realize when we do it in the next problem and when we do solve a problem. I have laid the foundation uh, for applying the element stiffness, or for applying the isoparametric formulation method for a rectangular plane stress element. We have done it in the conventional way, and now in the next lesson, let's apply this isoparametric formulation for a plane stress element to derive this plane stress element planes to derive the stiffness matrix for this plane stress element. Yeah, these are the equations which will be implemented in the finite element code inside the ANSYS when you run. This is the motivation that I wanted to tell. So without simply clicking the buttons, you should know as to what is really happening within this problem. And you will see that evaluating of the integrals of such elements having large number of degrees of freedom is not easy. For that, we will use special numerical techniques. We will quickly go through, let's say, Gaussian and Newton codes called quadrature numerical integration scheme, and see how these numerical integration schemes are applied for solving such complex problems.